Dear friends, I'm glad to see you. We're starting now our second day. And next report, Yuriy Drozd, please.
Thank you very much. Перш за все, я вітаю всіх учасників конференції. Так. Ну і постараюся зробити доповідь так, щоб всім було зрозуміло. So I congratulate all the participants and I will speak English. I hope that English is acceptable for everybody. Okay? Thank you. So I will start. Okay. So my talk is, the title of my talk is Morita equivalence of non-commutative Noetherian schemes. But first of all, I will discuss a bit the whole topic.
Ваша демонстрація не видно.
Так, це цікаво. Хвилинку. Зараз. Вони просять повторити. Добре, починаю трансляцію знову. Так. Кажуть, що пішла трансляція. О. Тепер видно? Алло.
Так, видно.
Чудово. Чудово. Отже, я почну з деяких таких загальних речей. Я нагадаю, перш за все, я нагадаю, про що йдеться? Йдеться про стару тематику, як пов'язані алгебра і геометрія.
Юрій Анатолійович, я перепрошую, можна на англійській мові, бо у нас є участь.
Oh, yes. I promised English, but started Ukrainian. So my talk is about the old topic, relations between algebra and geometry. The story is very, very old, starting from Apollonius, Descartes, and so on, but I will start from new age. Maybe I will record the old topic of Gelfand, or old result of Gelfand. There is one-to-one correspondence up to isomorphism, as usually. Between compact Hausdorff, of course, spaces and unital, which means with unit, commutative C-star algebras. Namely, X corresponds to the space of continuous functions. Okay. So, in your time, I will cite the result of 1962 by Gabriel. I will start with it because it also commutative. It's important. Let X and Y be Noetherian schemes. For instance, algebraic varieties. I denote Koch X, the category of coherent sheaths on X. Yeah. Then the result of Gabriel is that the two schemes are equivalent, are isomorphic, if and only if the categories of coherent sheaths are equivalent. Yeah. This is also a commutative topic. If we could deal with non-commutative objects, the result is quite different. And for instance, easy example. If we consider, say, a field K and the ring of matrices, right, they of course are not isomorphic, but the module categories are equivalent. This is actually, it can be explained for the students of the first year. Yeah. So in 1958, Kate and Morita gave a general result. If we have A and B are rings, then their module categories are equivalent if and only if there is, I mean that's left module because A to the left, they exist and write a module P such that, which is called progenerator. What it means that P is finitely generated, P is projective, and P generates the category of A modules. In this case, it just means that there is a surjection from some power of P, finite power, onto A. That's enough. Yeah. Our work with Igor Burban, it is, the paper has already appeared in Advances of Mathematics. Our aim was to combine the results of Gabriel and Morita and obtain a result for non-commutative Noetherian schemes. I will write non-commutative Noetherian schemes. What is it? Non-commutative Noetherian scheme X is a pair where X is a usual Noetherian scheme. For instance, algebraic variety. And A is a sheaf of OX algebras, a sheaf of algebras of X, which is coherent as a sheaf of X modules. Then we can consider the category of coherent sheaves over X, or the same, which is by definition the category of coherent sheaves over A. And even the category of quasi-coherent sheaves. In this case, quasi-coherent is just the direct limits of coherent. Yeah, in the Noetherian case. why this category is very good. It is locally Noetherian category. Which means good category, abelian and so on, and every object is a direct limit of Noetherian objects. And cohex just is the category of Noetherian objects from the category of quasi-coherent sheaves. It implies that the categories of coherent sheaves are equivalent if and only if the category of quasi-coherent sheaves are equivalent. Why do I need quasi-coherent? We will see that quasi-coherent sheaves are a bit more interesting, more convenient for us. Why? The thing is that quasi-coherent sheaves is a Grothendieck, as they say, Grothendieck category. I will not explain what it means. And in particular, it has, they say, enough injective objects. Enough injectives. It means that every quasi-coherent sheaves embeds in an injective. Then we have a good homological algebra and so on and so on. And moreover, we will see that when we will work, it is very important, we will work namely with injective models. Namely, I will denote by spectrum of X the set of indecomposable injectives in the category of quasi-coherent sheaves. Note that every, as it is Noetherian, locally Noetherian, and every injective is isomorphic to a direct sum of indecomposable. Infinitary direct sum, of course, in general. And moreover, this it is such decomposition is unique in the sense of Krugschmidt. Okay. So I will consider the spectrum. One more important thing is the notion of central non-commutative Noetherian scheme. It means that the center of this sheaf of rings is just the sheaf of regular functions of X. In general, it is not so. Yeah, it is the center of the contains in some sense, but it is easy, rather easy. I will not explain. This is for every non-commutative Noetherian scheme X, there is a finite map at X such that if we take the, let it be phi, the preimage of A on Z, it is also non-commutative Noetherian scheme, central, And the categories of coherent sheaves are equivalent. Of course, the Z is constructed locally. If we take an affine part, so it is just an algebra over some Noetherian ring, then we just take the integral, the center of this algebra, and it can be glued to the global finite map. Okay. Yeah. So it means that now we can consider only, so we can consider central non-commutative Noetherian schemes. The most important step is the reconstruction of the center. We have this XA, or this X. To do it, we use just the spectrum. So that we have some injective, indecomposable injective sheaf. Then it has the following properties. First, its support to the set of element of X such that this localization is non-zero is just the closure of some point. So all such points are just specializations of X, of some general point. So we have a map from the spectrum X to this underlying scheme X. The second point is that the pre-image, that I to this X0. The pre-image of every point is finite. Moreover, if I set Ix is the direct sum of all i's from the pre-image of X, of all i's supported at X, then Ax is an Artinian injective module over the localization over the stock of these sheaf of algebras A. Three, these sheaves are in one-to-one correspondence with maximal ideals of Ax. So if we have some maximal ideal here, then there is a unique sheaf Okay. And now we come to the most important things. Suppose that we have I and J two. And suppose that I is supported at X, J is supported at Y. Then first of all, there are homomorphisms between from I to J if and only if Y belongs to this support of I. Conversely, if I is from here, there are sheaves I and J, like above, such that there are homomorphisms between them. These are just algebraic facts about injective modules. And finally, this is if there is a homomorphism from I to J, and the endomorphism ring of their direct sum is Noetherian, then X equals Y. Moreover, this is if and only if there is homomorphism between I and J, and then the morphism of direct sum is Noetherian, it is equivalent to that they are supported at the same points. Now we can reconstruct X, not this underlying scheme. Let omega be a finite subset from the spectrum. Denote by I omega the direct sum of all injective objects belonging to omega. Yeah, and A omega the endomorphism ring of this direct sum. Then there is a point X such that omega is the preimage of X, if and only if the following two conditions hold. First of all, A omega is connected and Noetherian. Connected just mean in the sense of ring theory. It cannot be decomposed into non-trivial direct product, or it does not contain non-trivial central idempotency. And two, omega is maximal, satisfying the first condition. This is a maximal subset such that A omega is connected in Noetherian. So now we obtain the X is in one-to-one correspondence with such omegas. Moreover, we have already seen, we know the topology. Due to this condition. So we know when one point belongs to the closure of another one. It's enough to reconstruct the topology of Noetherian space. Okay. The more important and more question is reconstruct. Noetherian scheme is not only topological space, but the sheaf of functions. But it can be reconstructed as follows. Let Y is open, or this is X minus closed. Yeah. And then we can consider the restriction of our scheme onto Y, which is just here we have the sheaf of function, and here we have the restriction of A on U. It is also a non-commutative Noetherian scheme. Yeah. Then the category of quasi-coherent sheaves of X contains the category of quasi-coherent sheaves on X such that support is in Y. Moreover, it is Ser subcategory which means that it contains F belongs to this thing if and only if F and F prime belong to this thing. Okay. And moreover, yeah, if we have a Ser subcategory, then we have the Ser quotient. And it is equivalent to the category of quasi-coherent sheaves of this restriction of X on U. And then we have a functor from quasi-coherent sheaves of X here. And the functor has a right adjoint. It is just the functor of direct image, where I is the embedding of U to X. Okay. Then the main ingredient is the following proposition. Let our Y is the closure of a set of points. as the space is Noetherian, every closed subset is a closure finite set of points. Yeah. Then this thing, quasi-coherent Yx, is the smallest localizing category, subcategory, containing the direct sum of all I xi. That means of all in the composable injectors supported at the points x1, x2, xn. So we know this category, hence we know this category. What does mean we know? If we know the category of quasi-coherent shifts, then we know this localizing subcategory, and we know the quasi-coherent shifts on the localization of the on this restriction. And then one can prove that if we consider the sections of OX on U, then it is the center of the category of quasi-coherent shifts. I recall that the center is just the endomorphism ring of the identity functor of this category. Yeah. So we know, hence we have reconstructed X as scheme in algebraic cases variety. Okay. Moreover, we know when this U is affine. Which means that it is isomorphic to spectrum of some ring. It is well known that it is if and only if the category of quasi-coherent shifts, or or the same coherent shifts, contains a projective generator. It is well known that a category is equivalent to a category of modules of a sum ring, which is in a fine space case, if and only if it has a projective generator. Okay, so we know our scheme, we know affine subsets. Now we construct a sheaf P with the following properties. First of all, no. I have. Let now the category of quasi-coherent shapes on X is equivalent to the category of quasi-coherent shapes on Y. Then we have here XA, here we have YB, and we already know that X is isomorphic to Y, since it can be reconstructed by the category of quasi-coherent shapes. Yeah. So we have this isomorphism. It's, for me, is more convenient to do like this. Then we can replace XA by Y star K. So can think that X equals Y. Yeah. Now we construct coherent sheaf on X with the following properties. First of all, of right modules. First of all, for every affine subset of X, P, the restriction of P on U, is a progenerator for in the category of coherent sheaves on U. In a fine case, there is such cadet, and this is, must be PI. Then, if we have then there is an isomorphism of PV with the restriction from U to V of PU. Some isomorphism with gamma UV, such that gamma UV, and then we have restriction from V to W, if W. It is the same as gamma VW, UW, and gamma UU is identical. So we can glue O PU to P. It is called local progenerator. Local progenerator, this is just, it means that for any U, affine PU is a progenerator. So now we have the following result, the main theorem. X is isomorphic to Y. X is XA, this is YB. If and only if there is a local progenerator P in the category of coherent modules where X, such that there is an isomorphism that to be theta of B to the, there is an isomorphism. There are isomorphisms, y to x and theta of B to endomorphism ring to the phi, I beg your pardon, phi star, the preimage of the sheaf of endomorphisms of P. Moreover, this isomorphism phi has the following term. We must first take the tensor product with P over A. Take its preimage, which be an ring. This is this tensor product is a sheaf over endomorphism ring over P over the sheaf. Then we take his star, and then we take, it generates a B model. Yeah. So this is okay. That's all, and my time is also over. Yeah. Thank you very much.
Your time is over. Thank you very much. Thank you very much. Please, questions, comments.
So may I,
Please.
just to be sure that I understood the difficulty. So you said that the problem to recover X from the category of quasi-coherent sheaves,
Yes.
in fact, is equivalent to the same problem for
to recover the center from the category of sheaves over a non-Noetherian scheme.
Yeah, but why? So why you used in your construction to recover X the category of quasi-coherent sheaves, if I understood correctly, is just because the coherent ones do not contain the injectives. You don't have enough.
There are no coherent injective models.
So theoretically, one might be able to recover X from the category of coherent sheaves, but this cannot be done explicitly.
Yeah. You see, if we know the category of coherent sheaves, you can recover the category of quasi-coherent sheaves. Just
exactly.
Directly. So it is the same, but we must we work with injective.
Exactly. Yeah. Yes. Okay. Thank you.
Thank you. No questions.
I think that there are no.
Thank you very much.